So now let's talk about the position of the signal. And what I mean by that is where it lies on the x-axis of the spectrum. We call this the chemical shift, as we'll see. Remember, what we're actually measuring is radio frequency electromagnetic radiation. And it's being given off by the nuclei. In fact, initially it's absorbed. If you get into the details of how these machines work, a big giant blast of frequency is shot into the material, and then that excites everything. And then they slowly decay. Actually, I can show you that real quick. Let me go back in my slides a few. Remember that? There we go. Oops. So what happens is big blast, it starts to be, it lands down and then it circles back up to normal. That's what happens in reality. But that may be confusing to some people. But I just want to say that's what we're really studying is, and by doing that, all the nuclei are sending out radiation as they relax. Because if you think about energy or light, it is energy. Light is energy. And so if you're emitting light, you're losing energy. So you excite everything, and then as it relaxes, it's giving off radio frequency light, and that radio frequency, the frequency of it, the type of energy and frequency of the light is associated with all those characteristics about how much the energy levels are split, which has to do with the strength of the magnetic field that they feel, which while partly is due to the machine is set at whatever strength of magnet it is. So why is there any variation? Why do any of these signals appear at different positions? First of all, we have to point out that because there's different machines, we need to standardize it. Otherwise, if you use a 60 megahertz machine in one place and a 400 in another place, you're not going to have the peaks at the same numbers or values. So to standardize everything amongst all people who own some type of NMR machine, there's a standard that's picked. And the standard is TMS, which stands for tetramethylsilane, which is what this molecule is right here. And the way they standardize, and we're not going to really do this yourself, so you don't have to worry about applying it, but just you do need to understand at least the background of it, that's what we're measuring everything against. They set the frequency, or I should say, they set what we're going to call now the chemical shift, or the delta. We set that as 0 ppm. And then everything else is measured relative to it. So you observe the shift away from TMS, away from the peak that standard appears at when you take a spectrum. So it turns out whenever we do an NMR, we always put in a little bit of TMS. And then you measure the difference between the TMS and whatever the signal is in the spectra for your molecule, the different ones, many different signals. You measure where those signals are relative to the TMS in hertz, and then you divide by the operating frequency of the instrument in hertz. And so for this 600 megahertz, you divide by 300 times 10 to the 6 hertz. And then when you do that, you end up getting that value that it's in times 10 to the minus 6, which they just get rid of the times 10 to the minus 6 and call it ppm, parts per million. Okay, now we've zoomed back in to the way we should have it normally. And this is just showing some more, but let's just move past that, because the main idea is you should just understand that's why different machines would normally give different signals, because different magnetic strengths would have relatively different splittings, but we standardize everything. But why is there still different shifts, or peaks, I should say, for the different types of protons? So just some quick terminology. We're going to not worry about the background and history of it, but essentially this is something you should know practically, which is when you go to smaller ppm down here, we call that upfield. There's some historical aspect of it, but we won't get into it. It's kind of what's being talked about here, but it can be a bit confusing. But you just have to memorize and remember that when you go to lower ppm, that's upfield. When you go to higher ppm, that's downfield. I know it sounds backwards, but that's just how the terminology is. Also associated with it is the protons that go up, that are found upfield. The more upfield they are, the more shielded they are. The more downfield they are, the more de-shielded those protons are. And so when they're shielded, they're protecting that nucleus against the magnetic field. So it feels a smaller magnetic field, which means that they have a lower energy split. So essentially, upfield is lower energy, lower radio frequency energy that's being given off by that nuclei. And downfield, those de-shielded protons, they're feeling a much larger magnetic field, and they have a much larger energy split. So they are actually giving off much higher radio frequency radiation. So what's this de-shielding, shielding? Remember, we talked about what shielding was in the intro part, which is shielding is the electron density around the nucleuses. They protect them against the magnetic field because they generate generate an opposing magnetic field, the cycling of the electrons. So what happens is when you have electronegative atoms on the molecule, they withdraw electron density. We've talked about this in some other topics, such as polarity, and I'm trying to think of maybe a few other concepts that are just slipping my mind right now. The stability of acids and bases. And so electromagnetic electronegative atoms, they draw electron density towards themselves. If they're drawing the electron density towards themselves, they're pulling it away from other atoms. And particularly, as you can see here in this example, methane, those protons have a ppm of 1 for their signal, but as soon as you put an iodine on it, that electronegative atom begins to draw the density towards itself but away from those protons. That exposes those protons to the magnetic field more, which raises the energy splitting of those protons in their two levels and thus raises the ppm or the chemical shift. And you see that trend here. The more electronegative it is, the greater the shift down field. And then also the number of them affects it. You put a chlorine, but then you put 2 on, and then you put 3 on, and that even withdraws electron density even greater, so that it's even much higher down, much farther downfield. We see the distance effect here even. Here, 33 ppm, here 1.6 ppm for these protons, and here 0.9. So the chlorine has this effect that slowly shifts them down. You can even calculate protons. I'm not going to do this much in lab, but we'll do it for carbon atoms next semester for carbon-13 NMR. But for protons, there's also these set of tables that you can do. I'm just going to kind of flip past that for now, but you can actually calculate, and that's what that software I showed you, how it determines where the position of the peaks are, using some math and tables. I just want to quickly just explain there's one other great effect. There's one other effect than just electronegative atoms that changes the chemical shift, and that's what's known as anisotropy, diamagnetic anisotropy to be specific. But okay, forget all the fancy terminology. All it essentially means is if you have pi electrons, whether it be a double bond or whether it be a benzene ring where they're alternating around and they're actually all conjugated with each other. So it's a big giant ring of pi electrons. When you have that, the magnetic field, once again, just like electrons normally, gets them cycling around and generates an opposing magnetic field. But because they're in these pi orbitals, and especially the greater effect is when it's a benzene ring, it's in a ring of conjugated pi electron orbitals, so it can go all the way around. That's the way that the electrons rotate, is along those conjugated pi orbitals. All the way around the ring, they just start cycling and generating an opposing magnetic field. But where does that opposing magnetic field get generated? In the center of the ring is where it's opposing. But because, and this is something you may not know, but I'll just tell you, and it shows you right here, magnetic fields have to connect back. They can't just be a straight line to infinity. They have to be circular lines. They have to be circles. So you have to reconnect back to the beginning. And so these fields, like here, if you can see on the slide, they come back around, and in order to come back around, the arrow representing the direction of the field, it's opposing in the center of the ring, but then it's actually with the external magnetic field on the outside of the ring, and that's where most of the time protons are located. And so those electrons, where they normally would actually be having a de-shielding effect, those pi electrons actually amplify. They're not shielding, they're actually amplifying the external magnetic field that's being felt by the protons. So they actually push those protons further downfield, not because they're actually like the densities moved away from them, but because the density is located in pi orbitals that can cycle like this, they actually generate an amplifying magnetic field. So those protons feel a greater magnetic field. And so the splitting is greater, and so the signal for those protons is further downfield. You can see right here, this is where aromatic protons are located, much farther downfield than protons like these. These are probably the protons associated with this CH2 and with this CH3. And if you notice, these protons are kind of shifted downfield themselves, and that's because they're probably feeling it's probably tapering off with distance, just like the electronegativity effect. But they're still feeling a bit of an amplification from that anisotropy field that's being generated. So they feel a little bit of amplification, but not as much as the protons that are right there by the major part of that field that's being generated right here, right here. And then this just demonstrates it further that it is the idea that they're on the outside of the ring and that there's these magnetic field lines being generated, because protons that are inside of a ring that's having this anisotropy effect, they're actually deshielded. The protons that are in the ring they're deshielded more than TMS. That is to say, they actually feel a magnetic field even greater than the protons on tetramethylsilane. They're -1 ppm. They're shifted all the way upfield beyond TMS. And then the ones on the outside here, they're at 8 ppm downfield because they're not really being deshielded, but they're feeling a much greater external magnetic field than normal protons would. And this is a chart. There's other charts. I even recommend maybe some other charts on the line. Probably post one, at least in my lecture. Maybe Dr. Bay will also in hers. And then if you have Dr. Kim in the lab, maybe you can ask him. Maybe he'll post one separately too. But you can find many charts that just give you, and this is general rules. It doesn't mean you'll always find them here. It doesn't mean that certain molecules, for whatever reason, some other unique aspect of the structure further on down the structure might shift these outside of these ranges. But these are generally where you'll find the protons of this type, the ones that are highlighted in red. That's what the chemical shift is being said you'll likely find for these types of protons. So that's chemical shift. So let's go ahead and do an example. Let's go ahead and try a problem. So what we're going to do is just kind of look for our look for our chemically unique protons. So we've got this one is clearly different than anything else. It's right next to an oxygen. It's a set of 3. So we'll call that A. And then we'll call this one B. This is different because it's next to an oxygen. This one is a CH2 next to a C double bond O, so that's different than this one. So it's C. And then this H it's very unique because it's the only one that's by itself on a carbon, so that's D. And then these 3, hopefully you realize when you got this kind of split like this, these will rotate on top of themselves, and so these are identical always to each other. So that's a set of 6 of the same set, and so that's so we got D, A, B, C, D, and these are, I'll call these E. So we have these 1, 2, 3, 4, 5 peaks. And if we look at the spectra, right here, then we can clearly see that it does have 5 peaks. It's got 1, 2, 3, 4, 5, or excuse me, not peaks, I'll say signals. So there's 5 signals. We should expect 5 signals for this. What are their positions? Now, obviously, 6, 1, 2, 2, and 3, the integration will help a lot. But we're not going to, let's say we don't, for whatever reason, we don't have the integration. We still always have multiplicity. You'll always see that, but you don't always have integration values. So what we're also going to look at is the chemical shift. And so what we see is these 3 are far away from any really electronegative thing except for the C double bond O. Whereas these CH3s, they are right next to an electronegative oxygen. So these 2 right here should be relatively far downfield. Now, there is this double bond nature, and that normally affects the the proton positions of things, and so those are probably the next ones that are downfield, are the ones here, because they're feeling that effect of not only the anisotropy and the field that's being generated through the rotating of the pi electrons, but it is also a pretty electronegative, or has this polarity that's drawing electron density away from it. So we're going to expect these probably to be the next further downfield. Or excuse me, these are the most downfield, and then these are the next 2 that are probably downfield, the next set that are downfield. And then this one group is probably pretty far upfield, because it's not really near anything, close to anything that much electronegative. Now, Obviously, multiplicity. Let's just go ahead and take some time to do our multiplicity real quick. So these H's have nothing neighboring them. Because remember, it would be the neighboring carbons to these protons, or at least neighboring to the carbon that has these protons, that you would look to see what protons they have. Those are the ones that would be vicinal. These protons are not vicinal to these because in order to get there, you would have to go the bond that's connecting the hydrogen to the carbon, that's 1, 2, 3, and then the next bond that connects this carbon to its hydrogens would be 4. These are not vicinal to this. So there are 0 vicinal protons to this, so it should have a multiplicity of 1. 0 plus 1. These ones, they have these 2 vicinal to them, so they have m equals 3. These, same thing, they have 2 neighboring vicinal protons, so they have an m equals 3, so they would be triplets. So 2 triplets, a singlet, and then this one right here, this one, it has 6 vicinal protons to it, and so it should actually be a septet, or m equals 7. And then these 6 protons, they only have 1 vicinal proton neighboring to them, so they should be 2 is their multiplicity. Oops. I was naming it in an earlier cut of this, and I decided that was too much time. So m equals 2, and so they would be a doublet. Not even looking at integration, although sometimes you may get it, sometimes you don't. Take a look at the, let's go back to the spectra. And if you look at the spectra, you'll see that, yeah, there is a triplet, a singlet, another triplet, a septet. And it's a little hard, so let's zoom in a little bit. You can kind of see them as we zoom in. 1, 2, 3, 4, 5, 6, 7. So there is 7 there. And then, right over here, there's a doublet. And that makes sense. And then the order, if you notice, makes sense. The 2 farthest downfield are a triplet and a singlet. And that's what's right here, triplet and singlet. Then the next 2 farthest are a triplet and a septet. A triplet and a septet. And then the one farthest upfield is a doublet. So like I said, this is kind of a qualitative thing. Will it always make sense? Will there be some ambiguity? Yes. I'll try to make the problems you get in the worksheet and on the thing as most straightforward as possible, but sometimes you just gotta, there'll be enough information to know the right answer, but there is sometimes where it's just kind of, you kind of have to just know what all the options are and narrow it down based on the data that you have. Next, we'll finally do one just straight up unknown solving problem on the next video. Bye.